warmly inviting me and supporting all the coordination work to host this virtual inaugural talk in data science theorist talk, actually. So let's start today's talk by getting back to the history. So in our testing, actually, we have a 1,500 year of the history of tests. So the first starting from the empirical examination in China in Sui Dynasty. And at that time, it's only a kind of an essay writing. So, and emperor just to be the final great evaluator to see whether the essay is correct or not. We'll give a kind of a score there. But things actually develop into more standardized testing. For example, in the high school, students take the first year National Merit Scholarship Program exam in 1973. So that is the first time we want to use the standardized test. So based on this kind of history of a test, we continue to have the new era. So history continues. I just used Professor Huahua Qiang in his recent paper in 2021. He mentioned in the sentence in his paper, he said, modern theories in measurement with tremendous data sources are rapidly transforming testing from unaccommodated measures into informative tools that can be used to address various challenges in today's teaching, learning, and assessment. So you can see actually tremendous data sources are very important in currently. To just give you a kind of example. Because when I at ETS, I do quite a lot of things for international large-scale assessments. So PISA dataset is a kind of a very familiar area for me. So assume that in PISA 2012, at that time, we'll only have 45 countries. Each country will have 5,000 students at sample size. Each student will take 100 items. The 100 items including the assessment items, cognitive site, and also the survey questionnaire. So we just give a kind of broad, roughly estimation at that time. At that time, the data point is 22.5 million. But continue on to the PISA 2022, we have at least 90 countries in the world to join PISA. Each country still have 5,000 students at sample size. Each student will do 100 items as the same as before. But students, because we come into the computer-based testing and then we can capture more data then. So assume each student will have 10 times transitions and 20 actions and time point per item. So that number becomes 9,000 million data point. You see, within 1 decade, that is 10 years. So our data actually enlarged by 400 times. So we still can use a traditional psychometric modeling to help us to do this kind of cognitive estimation. But at the same time, we also need some new methods and to treat this kind of big data set to make the purpose for our educational assessment. And also, the item is changed during these the past 10 years. We can see actually examples come from different subjects. For example, we not necessary to only have the yes or no or multiple choice item or traditional open-ended questions, but we have quite a lot of interaction items that can capture more for the students, especially in their daily life. For example, the first picture shows the NAEP in 2017. We have the grade 4 students use an interactive math example item. So for this item, students can drag and drop different parts of the letters into this cell, and also they can use the calculator to help them to calculate what's the percentage they should put down there. In 2018, so that is the first time the IEA conducted for the computational thinking interactive program. So this item is a kind of a coding example item. So you can see the students actually can build up the coding in the simulation environment to control a kind of a farm drawn things. And students during this process, they will figure out to say what kind of codes they need to put into this kind of testing area. At the same time, they also figure out whether they need to use a sufficient way. For example, whether they want to put into a loop function, for function, like this kind of thing. And 2015 in PISA, we also have the collaborative problem solving example item. So you can see actually students not only to choose which one will be the optimal conversation from the test, but at the same time, he can use their there are different ways, use the different actions to click on different map and to get a better feeling to say what kind of a conversation should be going on in this kind of test. So currently, OECD and IEA and also the NCES, they build up quite a lot of new, this kind of interactive items. So that gives us a kind of a new opportunity to use this data, but at the same time, also we will have some challenge over there. Let's see this is a typical assessing process. From our traditional psychometric model, also we can do that. Basically, we have a person level characteristics and also test level characteristics. So based on these two parts of the information, we can get students' response. So the response is kind of results of the task completion. And we can see from the person level characteristic, we can add into different information there. We can have demographic, we have personality, we can have a speed or motivation. And from task level characteristics, we can include the item type, item format, item difficulty, item position, item wording. So all these kind of aspects can be contributed to your item and then to your estimation, right? But at that time, because when we use the paper pencil based test, we don't include all the things in this kind of black box. The black box actually is this completion process. So that is what capture the students how they do during this process. That is only can be done in the computer-based thing. So in the computer-based thing, that help us to make it in a complete loop. We have not only the person level characteristics, task level characteristics, but also their process. And based on all this kind of information, we can make a better estimation for their results of the task completion. So let's see deeper into what is in the black box. So basically, when we have the psychometric model, we have theta, so that is our latent trait, right? We want to estimate that. How can we estimate? We can use the responses. So that is our observed variables from the responses. Theta can be represented by your observation. When we have the black box in the completion process, so we come into the process data. Process data is a kind of new sources of your observations. We can call them as YP. So that is your new observation from your process. So we give them as observation from the process data. So the process data is an enormous amount of unstructured data. And generally, we will focus on the performed actions and associated timestamps. And at the same time, we also can see this function of a process that shifts from merely debugging as a byproduct in assessment to a more efficient way to provide a comprehensive profile for the test takers. And if we want to do some analysis on the process data part, so that calls for new methods with incorporation of data science and analytics techniques to reshape the future of measurement. Then we can summarize to say, why does response process matter? We can summarize them into 5 perspectives. The first one is task construction, because generally for example, when we at ETS, we want to build up better task for the students to get a better estimation of their latent trait. So we have investigating if examinees interact with tasks as intended. The second one is invariance explorations. So that means you want to define the invariance between the group, not only by the item difficulty. For example, we use a diff, we understand whether item difficulty is different from different groups. But at the same time, you want to check whether they have a different problem-solving process and strategies. That could be important, especially when we come into the equity and fairness issues for the test. The third perspective is richer description. So we want to investigate if examinees could solve a given task and show efficiency they did. For example, if the students use different solutions and use different efficient ways to solve the same problem, whether they should have the same latent trait. The fourth one is refining our theories. That could provide new evidence for cognitive process that could not be captured from paper, pencil-based assessments. The final one is the tailored interventions. So generally, we will have the adaptive testing from CAT. Professor Hua Chang is a real expert in this area. So we use the CAT, these kind of techniques, but at the same time, we want to include more information from their process. So we can identify sub-skills or meta competencies that examiners are lacking. So today I want to base on all these kind of background questions and then come into how we can use this kind of sequence-based methods in process data analysis. So basically, currently in sequence-based methods in process analysis, we can divide them into three important perspectives. Because our process data looks quite similar like language-based things. For example, text and click streams are commonly encountered types of unstructured sequences data. So borrow from the sequence mining, natural language processing, for example, NLP, and the machine learning, and even currently we have a large language model, for example, from BERT model, or even more generative AI models. We can put them into our sequence analysis for the process data. I divide them into three perspectives. The first one is we generally can put the long sequences into the mini sequences. For example, like n-grams. Using these methods, we can disassemble long sequence into manageable short pieces that extract it as features in prediction and clustering. The second one we name is a sequence similarity measures. That take the sequence as a whole, not chunk them into small pieces, but actually we calculate them as a whole piece, compute the distance between each pair to create new variables for prediction and clustering. And third one is latent sequence modeling. So latent sequence modeling is from our observed sequence to derive the latent sequence transition stages and the probabilities. So let's come into these three perspectives one by one. So the first one is the mini sequences. We put them into the n-grams. So n-grams is quite familiar with everybody because when we come into the text mining or natural language processing, so that is the basic factor we will capture. So for example, I'm happy to give a talk today. So generally we will have the unigrams. So that is one word as one kind of core things into your mini sequence. And we have bigrams, for example, I am, I'm happy, happy too. So every two adjacent words will combine together. So similar as in our process in the sequence. And then we have trigrams. So I am happy, I'm happy too, happy to give a talk. So that is a trigram. Every three adjacent words will be combined together. If we put them into the action sequences, for example, in PIAC, one action sequence can be the students come in to start, and then he click into the spreadsheet environment. He type into the full name of the keywords that he want to find information from the spreadsheet. And then he click into the email page. And in the email page, he uses sending. And finally, he can next, okay, and end the whole item. So that is quite a typical kind of action sequence you can capture from one item, from one person. So based on that one, if we chunk them into small pieces, we can see actually we have unigrams, 8 unigrams, and 7 bigrams, and also 6 trigrams. So that is easier, you just chunk them into small pieces. And then based on your small pieces, we come in to give some different weighted frequency. For example, we can put the weights like into the natural language processing, we call them a TF-IDF. But in the action sequences, we can put them into a different name, but that will be similar methodology there. The weights generally will be divided by 2 parts. One is dampened term frequency, and the other one is inverse sequence frequency. So inverse sequence frequency, these parts actually tell us if everybody uses the same action. So this action, the weight will be very small. It's similar like a stop words in the text mining. And the other part is temp the term frequency. So that actually gives you kind of adjustment about the term frequency on how many times one person used the same action. If the person uses 3 times of the same action, that should be different weights for 3 different people use that action for only 1 time. So we will follow this kind of formula to get a kind of weighted frequency. And then we can base on different feature selection model from the machine learning or from the other way to get what will be the robust features to distinguish by different groups. For example, the very straightforward one, we can choose using chi-square feature selection. And For example, we can put all the people's actions into the correct group and incorrect groups. And by each layer over there, that can be by different countries. For example, we can have a Japan, Netherlands, the United States, but different countries, they will have a different features there. But if we use the aggregate level as a correct and incorrect, so we just follow the chi-square feature selection model and to find which one will be the highest one. And to based on the highest chi-square feature selection model, so we can have the more discriminative in the classification. But if we change this cube into another angle, actually that you can see, we can also compare the features by each country against the other countries in this test analysis. So I can show you one example that's in a paper of me and written together with Matthias von der Veer in 2016. So that is the features of actions by performance groups, by correct or incorrect groups. We can find we have unigrams, bigrams, and trigrams. So in the correct group, we can find the chi-square value is pretty high, like they say using the tools such as a searching engine and a sorting with a very clear sub-goal. You can showing this kind of up by using the grams. But at the same time, we also can find in the incorrect group, we have the hesitant behaviors using the cancel this action quite a lot. And also we find the incorrect group that they're using help function a lot and aimlessly save the results in the server. At the same time, we also can find the non-responses pattern. For example, they just click on start, next final ending as a non-response, but actually we'll put them into the incorrect group when we estimate for the PIAC, that kind of, especially for their problem-solving items. So another one is we can see the features of our actions by different countries. So just now we see the cube, actually you change the other angle, we can compare with the United States against the other two countries or Netherlands against the other two countries. So here actually we can find in the United States compare with the other countries. And so the robust features in this group showing up by the double clicks on the email page. In the Netherlands, we also can find that it's more likely use the full name, and the given name is when they are doing the searching using this kind of engine. And in the Japanese group, we find, it's very interesting for the Japanese group, actually, we find spelling mistake as a kind of robust feature in this group. And we double check, is this because there is a kind of optimal space between the first name and last name. As we all know, if we have the characteristic-based language like Chinese, Japanese or Korea, not necessary to have a space in between the first name and last name. But in the English, like this kind of alphabetical way, so generally we will have the kind of space in between. So for Japanese group, actually we find this kind of spelling mistake generally contributed by this kind of space between the first name and last name. And that is our test design have the problem, because in our test design, we say this in the Japanese version, even though that is a character-based language, we still need to have the space in between. So you can find quite a lot of students actually they do not know this kind of a space in between. So just keep writing this kind of typing in as a kind of their searching engine. But you can also find finally they find this kind of problem and they change their strategy over there. If this kind of issue can be found in the field trial, that would be really great to avoid this kind of things happen in the main study. So the application of the mini sequences actually from the n-grams can really benefit from two perspectives. The first one is for the test development. We can quickly check the robust actions by correct or incorrect groups, and also identify the key actions used by groups with a different background. For example, by gender, by race, by different socioeconomic status, for equity and fairness checking. And also at the same time, the teacher can use this kind of information to dynamically compute occurrence of actions withdrawing the likelihood, similar as large language models, to predict whether students can on a good track. And also adding the time pauses as an action into the n-grams to identify when and where the pause occurs and associate the before and after which action. So second methodology we use in the sequence analysis is use the sequence similarity measures. In the sequence similarity measures, we generally have sequence similarity measures, predefined sequences, or pairwise. So for example, in the longest common subsequence that I did research in 2021, so that is we do have the predefined sequences from the test developers. So based on these methods, we can make a comparison to see how far away each individual will be away from the predefined sequence. And the second one is named the added distance. At the same time, sequence similarity with incorporation of timing information, that is our current study, we also can do like that. For example, we can incorporate an elapsed time with the longest common subsequence to see if not only consider about their action sequences, but also consider about the time in between each actions. So what will happen for the clustering or prediction. And also we can use dynamic time warping methods. And currently we are working on using the spatial temporal trajectory similarity measures to calculate action sequence and also time sequences in between. The distance measures and also the latent feature extraction is also a kind of a branch into the sequence similarity measures. So we can see we use the distance measures and the multidimensional scaling for parsimonious descriptions of behavior patterns. That is first did by Dr. Tang in 2019. So that is a very good paper published in Psychometric. I show all the references in the last two slides in my talk. So actually you can have all these kind of references there. And also currently some new study is working on using deep learning methods from observed sequence to obtain latent sequence features. So today I want to highlight only two parts of the similarity measures here. So the first one I want to highlight is use the longest common subsequence because it's a kind of a basic foundational methodology in the sequence analysis. Longest common subsequence can also be a kind of a basic things for the spatial temporal similarity measures. So let's come into longest common subsequence a little bit more. So generally we want to find longest common subsequence between two sequences. Let's say we have xi and also we have a yj, these two sequences, and by their order of each elements within the sequence, we want to see how many the longest common things can be found in these two sequences by different this kind of formulas. You can calculate that. To show you one example here is use the longest common subsequence as computations example. For example, we have 4 observed sequences, and we have that is reference sequences. For example, like to say just I want to mention here, if we have the longest common subsequence come into the predefined sequences to make the comparison. So sometimes you can imagine the predefined sequence for one item that can be multiple. So not only one solution can do this item, but actually you can have multiple solutions to solve out this problem. So here the example shows if in this item we have 4 predefined sequence, so that means equally these 4 solutions can get the final correct answer. And then we can come into one observation for this person to solve this item. And so we use the observation, this sequence compare with each reference sequence and to see which one actually has the longest common subsequence with the longest length. And that is more likely this person will take that solution to solve this item. For example, we calculated this observed sequence against these 4 predefined ones, and we can find the final one, the longest common subsequence, like length equals to 9 is the longest one. But that is actually, it is most likely this person will use this strategy. But actually there also have some things that we need to note, and also we are currently working on, because we do find people will showing up a different membership into different ways. For example, if people, when they solve the item, they will use one solution first, and then they use the other solution to make a double check. And so that means this person not necessarily only use one solution to solve it, but actually use 2. So that should have a kind of a multiple membership inside. So that is more complicated than only we use a single likelihood for this kind of case. But based on this kind of computation for the similarity, actually we can get a kind of new indicators. For example, we have similarity or efficiency. In the similarity part, actually, we can find we use the longest common subsequence divided by the length of your reference sequence. And where you have the efficiency, you use the length of the longest common sequence divided by the length of the observed sequence. So from efficiency way, that is to say, how many redundant words or how many redundant actions, not necessarily used, but you still use. So that will showing up in the efficiency indicator. So for example, in 2021, in our study, and we find for the similarity, actually, that they have a very high correlation with their performance in the problem-solving items. You can see actually by different level of the people, and we can see their similarity score actually showing up by the, like to say, the highest level people, actually they will show similarity pretty high with the predefined sequence. But for the efficiency way, actually, we also find generally people, if they want to get a high performance, they will use more redundant actions. For example, like this group, actually they have showing up the highest performance, but actually they use not that efficient way to do that. So that means generally high level people will use more redundant way to solve the items. And I want to highlight the second sequence similarity measure is named the dynamic time warping methods. So the dynamic warping methods actually is a kind of way different from Euclidean sequence we generally calculate. We generally calculate by sequence similarity. It is one data point to the other data point in I and J, right? But in the time warping, a dynamic time warping methods, actually we allow to say one data point can be matched to multiple points in the other sequences. Why we want to do that? It is because when we have sequences without the same length, and or they are showing us the same patterns, but actually just because they are putting on into the different time window. So in that kind of case, we calculate if we calculate it by the Euclidean methods, you can find that their similarity is very low. But actually, if we use the dynamic time warping, they still can capture the shape of the sequences, but actually just consider about they are happening into different time window. To show you one example like that is we can calculate use the DTW methods to calculate the visit and revisit or navigation, this kind of sequence distance. For example, the first one is a normal pattern. The students generally, the blue line is our standardized one from item 1 until item 26. But the students, each individual student becomes the red line. So you can see the first one is the normal patterns. So the distance between the predefined, the normal one and this individual one will be very, very small. And then we also find the students with multiple back and forth revisit pattern. So in that kind of way, the students will use longer sequences than our standardized one. So in DTW methods, actually, it can calculate the similarity for this kind of a case. And the third one is you can see the double review patterns showing up by the students. They finish all the items and then they come back to the very beginning and then do it. And the final one is the quickly skip patterns. So students didn't finish the whole patterns, the whole items, but just stop in between. Using this method, we also can calculate the time sequence distance. For example, the same set of items, we can say that is test late, and the blue line is the medium level for the correct group. But you can see the students actually, for the first student, the red one shows at the beginning, students use a little bit longer time to get used to this kind of environment, and then quickly he follow all the patterns there. But for the second student, actually he used extra longer time at a couple of first questions until he come into the fourth item, he can come into normal things. So for that kind of way, if the teacher can follow this kind of actions, the teacher can actually very clearly understand where they find this kind of problem, or the students probably can get some block there. And currently we are working on the process data supporting the ICLRS, the measurement over there. For these kind of a programming code questions, actually, it's very interesting to find more than two-thirds of students actually showing up the missing responses here. And we want to use the process data to figure out to say why the students showing up this kind of missing value. So that is non-response patterns showing up use the DTW. So we can see, interesting to see the class of 30 students. Actually, they just miss up the first two questions because that is very high as a 9, and the other ones actually have the real score here. So that means that this student didn't read the instruction and don't know the first two items is not kind of warm-up questions, but actually they also calculate into the scoring. And also cluster 4 is very typical. You can find students just skip, they find it quite difficult from item 5, they just skip all the things from 6 to the 9. And also we have students, they work hard until the item 8, but just skip the last. They think that is the most difficult one. So the third one actually the methodology related to the latent sequence modeling. So latent sequence modeling is generally you can observe the sequences and come back into the latent way. So especially when we can use a hidden macro model and to help us to provide some probability to compare by different transition probability and also emission probability. So for instance, that is a hidden macro model. We can have the Y1 until Y4, that is all our observed actions. And also based on this kind of observed actions, we can come into the sequence, latent sequence to see by different stage over there. So for instance, we use into the PIAC data set and we find in the high literacy correct group, actually they're showing up a special stage out compared with the others because they use the sorting this kind of stage. And that is cannot find in the other literacy group. And also we find, even though in the incorrect group, but for the low literacy level people and the high literacy people, when they go back and forth, showing up this kind of hesitant behavior. So they were using different stage. For instance, for the high literacy group, they will come back to, even though they click on come back to redo this item, actually they will do very clear goal to check what kind of tools they haven't used before. But for the low literacy people, actually they go back to see their state, latent state actually is kind of messy. They will randomly go to different states. And at the same time, we also do the analysis using put elapsed time in between the sequences and to see whether our latent state can show where actually students have the long pause or short pause area. So for instance, in the cluster 1, so that is a high ability per people. So you can see high ability people, actually, they are very clear to show after they come into stage 1, they will come into the pause time. The pause time, actually, they want to check what is happening in this item. And after they do the first state, they will come into the pause again and to have the double check. But you can see the cluster 2, that is a low level people. Actually, they go back and forth quite a lot of time, but different states of the pause stage. Okay, let's come into some discussion about my study overall over here and to share some outlook about my thoughts for the future study. So some thoughts for the process data studies in the future. That is kind of reimagining assessment framework. Because after we do quite a lot of study from the process data, especially we have the feeling to say the challenges from the AI, especially when we have the ChatGPT, that is mainly on the response data. So process data may add more weights in assessment model in the future to compensate the risk of AI manipulation. Because we hear something like to say we use a ChatGPT, can do the PISA, can do the TOEFL, or can use a ChatGPT to do the GRE and do very good job in there. But actually it is because we only based on response data to get a score for TOEFL, for GRE, for what kind of a test over there. So actually that is a kind of perspective to capture, make the estimation for students, their latent ability. But at the same time, the process data can give us more information there. So why not to keep them also into our assessment, into our estimation? So probably that can compensate the risk of the AI manipulation over there. And also currently we can use the generative AI models for better measurement especially put into the process data. For example, a recent study in my lab is to predict the missing data with the process data in the large language model and the BERT model. That can result in a significant improvement, especially for the highly difficult item with diversified solutions. Because typically in this kind of item, you will have many ways to make things wrong. And so if you use this kind of big large language model to capture this kind of information, to make a prediction for the missing data for the items that the people just skip away. So that will be kind of a good way to showing up the generative AI models in a better measurement. And the other perspective it is to say, one-time assessment is not the target of education, but tracking the students' progress and providing timely and helpful supports that will be more important. And we do think a process data could be given a broader scope for dynamic and longitudinal study. And the post-assessment process analysis could be progressed to dynamic process data analysis throughout the assessment. It could be a new trend in the future studies to bring new meaning for adaptive testing. So not only from the responses, but also from interactions. So just to give some inspiration for the future study. And so here are the references list I use in my talk today. And finally, I would like to say thank you very much for your attention to my talk, and I appreciate all the questions and suggestions. Thank you.
It was excellent. We really learned a lot. Yeah, from your talk, what we learned is now, even though we have these generative AI like ChatGPT, but data analysis is still the most important thing for us to solve the problem. So if you don't have the skill to analyze data, then I think these tools should be just like a black box. And now we have a few minutes left. If audience have any questions, you are welcome to ask. Yeah, or we can, just because this is our first talk, our series consists of 5 talks. For each talk, we will, post our video. Today we recorded, and we thank Professor He for her generosity. Not only made such an excellent presentation, but also, allow us to record her presentation.
Yeah, sure. So yeah, because I put my email over here, so if you have any questions, you can feel free to write me email and to see whether there are some things we want to make a further discussion.
Okay, thank you. Thanks everyone. Particularly thank Professor He for your excellent presentation.
Thank you so much. Thank you. Thank you, Professor Chang, to invite me here. And yeah.
Thank you very much, Dr. He, for giving us an excellent presentation.
Audience says thank you very much.
Oh, sorry. I mean, because the process data is it's kind of a new field, but actually more people can use on that more and more. So if I have any questions or suggestions for us, so that would be really appreciated.
Our next talk will be March 26th. We'll invite a professor from East China Normal University, and he will discuss something also about how to use psychometrics to help large language models to rate students' essay. And we will, keep you informed for all the talks. Thank you very much.